Hello, everybody. Welcome to week 9. So our theme this week is still group actions. We're in chapter 3 of the lecture notes. And our goal today is to prove the Orbit-Stabilizer Theorem, which is the main theorem on this topic. So to do so, we need to just recall a little bit of the viewpoint that we had last week regarding group actions. So the concept of group actions, really, in a sense, it's almost more about a viewpoint or a widening of our view about what groups are and what they do, rather than any major new theoretical elements. So when we talk about group actions, we're thinking of the elements of a group as being actually sort of dynamic objects that do something, rather than just sort of inert objects with their own algebraic structure. So in the context of group actions, every element of a group operates as a permutation of the elements of some set. Okay, so an example, which I think is a really good example to go back to when you're thinking about this viewpoint, is take something like the groups of symmetries of our regular polygons, the dihedral groups. So if we're talking about, let's say, the group of symmetries of the pentagon, D10, we can think about the 5 vertices of the pentagon. And every element of our group is a rotation or a reflection of the pentagon, and it moves those vertices around, it permutes them. Okay, so we could say that the group D10 is acting on the set of vertices of the pentagon. Its elements move the vertices around. Okay, so that's a kind of good, relatively concrete example of this phenomenon. The general setup is we have a group G. If we say that G is acting on a set S, what that means is that each element of the group G operates as a permutation of the elements of S. So symmetries on the vertices of a polygon is a good example. The notation and lingo that goes with this, the element G, it acts as a permutation on the elements of S, and if X is a particular element of S, we would denote its image under the permutation arising from G by G dot X like this. And so if X goes through all the elements of S, then G dot X does as well. G shuffles them all around. Okay, it permutes them. There are a couple of things that we insist on that a group action should do, basically respecting the fact that the group G is not just a collection of permutations of a set. It has structure. It has an algebraic structure of its own. So one thing that we insist on is that for an action to be properly defined, that the identity element of the group should act neutrally on the set. So that the identity element of the group should leave every element of the set alone. It should act as the identity permutation of the set. That has to be stated. It's not automatic from just saying that every element of the group must act as a permutation. So it needs to be included in the definition. And then the second thing that we require is that if we take an element X of our set and we hit it with the group element H, so we get a new element of the set, which we can again hit with a different group element G to get an element still of our set S, that the result of applying H and then G to X should be the same as if we applied the composition GH in the group to X in the first place. Okay, so the GH here means the composition of G with H in the group G. The dots here mean the permutation that we get by first applying H to X and then applying G to that. Okay, so we want the composition of permutations on the set to respect the group structure, the group operation. Okay, so those are the two conditions really that a group action must satisfy. And then once we have all that set up, related to any element X of our set S, we have its orbit. Okay, and the orbit of the element X is the subset of S consisting of all those elements of S that can be obtained by applying group elements to X. Okay, so again, if you go back to the example of the vertices of the pentagon and the dihedral group acting, if you take any vertex of the pentagon, you can find a rotation, for example, that will take it to any other vertex. So the orbit of the vertex you started with then is the full set of vertices in that case, but it can be smaller in general. Okay, a couple of observations about orbits. So the orbits are subsets of S. S itself in general doesn't have any algebraic structure, it's just a set. So now these orbits, the orbit of any element X is a subset of that set S. A couple of observations about that. First thing is we can say for sure the orbit of X is not empty because X itself is there, since X is obtainable from itself by hitting it with the identity element of the group. So every element X is in the orbit that it determines itself, G dot X. Second observation, if we take two elements X and Y of our group G, we might ask ourselves, how do their orbits resemble each other? If they're both subsets of S, what can we say about them? Well, the first observation is if Y happens to be in the orbit of X, which means that there's some group element H that when you hit X with H, you get Y. If that happens, then X is in the orbit of Y as well, because you can hit X with you can hit y with H inverse and get x. So in that case, the orbits of G and X are actually going to be the same set. Okay, y is obtained from X by hitting it with something in H. Then everything else, everything that you can obtain by hitting y with elements of G can also be obtained by hitting X with elements of G. So in the case where y belongs to the orbit of X, the orbits of X and Y are actually the same subset of G of S. And in the alternative case where y doesn't belong to the orbit of X, then the orbits of X and Y turn out to be disjoint. They have nothing at all in common. Okay, so we've got a bunch of elements of our set S. Each of them determines an orbit. The orbit determined by two different elements can be identical or they can be disjoint, but they can't partly intersect. Okay, and that means as we go through the set S, at least if it's a finite set, we get we can look at the orbits determined by each element. Some of them coincide, some of them are entirely separate, but if we just take the distinct ones, so like one copy of each of the orbits that arises, what we get is a partition of the set S into a bunch of disjoint pieces, which are the orbits of S under the action of the group G. Okay, so if we have a group G acting on a set S, that basically means we have a partition of the set S that comes from that action into separate orbits. We've seen how this works, for example, for cyclic subgroups of the symmetric groups consisting of permutations generated by a particular element. Okay, that's the context and the language and the setup. Okay, the other ingredient that goes along with orbit is the concept of the stabilizer of an element. So, same setup. X here should be an element of S, not of G. Apologies for that. I'll fix it in the version that I'll post with these slides. X is an element of the set S. The stabilizer of the element X, which is denoted by stab for stabilizer in the group G of the element X, is a set of those elements of G that leave the element X alone when you hit it with them. So the stabilizer of X is a set of elements of the group G with the property that when you hit X with that element, you just get X itself. It's a subset of G, of course, excuse me. It's a subset of G. That right curly bracket also is extraneous and shouldn't be there. Okay, so this is the subset of G consisting of those elements of the group that leave X alone. Okay, and the lemma that I mentioned last week, but we'll have a quick proof of it now, is that this thing is not only a subset of G, it's a subgroup of G, and that follows from the definition of a group action. So, stabilizer of an element X is a subgroup of G. How are we going to prove that? Usual setup for proving that something is a subgroup. Three things to do. Show that the identity element is there, show that it's closed under the operation of the group, and show that whenever we have an element there, its inverse is also there. So first, identity element of G stabilizes X. That follows from the definition of group action. Okay, that's built into the definition. Okay. Second thing, closure. So suppose we have a pair of elements of G that stabilize X. We need to show that their product in the group also stabilizes X. So we need to look at what GH does to X. Well, fortunately, because we have a group action, we're able to do something here. The information available to us is that both H and G separately stabilize X. When we hit X with GH, we know that that's the same as hitting X with H, and then hitting the result of that with G. H is in the stabilizer of X, so H dot X is just X. So this is G dot X. G is in the stabilizer of X, so G dot X is X. That's what it means to say that G is in the stabilizer of X. So our conclusion is that GH hitting X just gives us X. In other words, GH stabilizes X, and the stabilizer of X is closed under the group operation in G. Then finally, we need to show that if we have something that's in this stabilizer, its inverse is there too. So we give ourselves an element of the stabilizer of X, and we think about what its inverse does to X, and hopefully we'll be able to deduce that its inverse is also in the stabilizer of X. Okay, we know that G stabilizes X. That gives us this equation, G dot X equals X. If we hit both sides of that with the inverse of G, we can cancel the G on the left, and we pick up G inverse dot X on the right. That's essentially the proof. So hit both sides of that with G. Going through the steps here. G inverse applied to G dot X. We know that the G inverse in G can be composed here. This is the identity of G applied to X equal to G inverse applied to X. We also know that the identity element of G is the stabilizer of X. That's in the definition of a group action. So this is just saying X is equal to G inverse dot X, which is exactly what it means to say that G inverse is in the stabilizer of X. So the stabilizer of any element in a group action is a subgroup of the group that's acting. This is useful because it means that stabilizers are not just amorphous subsets, they have algebraic structure, and it means we can apply Lagrange's theorem, and we can sort of make use of some of the knowledge that we have about subgroups and some of the type structure that goes along with them. Okay, our main theorem, as promised, is the Orbit-Stabilizer Theorem. And what it does is relate the number of elements of the orbit of some element to the index of its stabilizer in the group. Okay, so the setup is we've got a finite group acting on a set S. For any element X in the set being acted on, to think of a vertex of your pentagon, dihedral group of order 10 acting, the number of elements in the orbit of X is the index in the group of the stabilizer of X. Okay, so there's a lot of language here. What does this say? It's saying I've got a group acting on a set S. I've got an element of my set. I want to know if I hit this element with all the elements of the group, how many different things do I get? What this is saying is that the number of different things that I get is the number of distinct cosets of the stabilizer of my element in the group. The stabilizer of my element is the set of things that leave it alone. The order of the stabilizer is the number of things that leave it alone. The index of the stabilizer is the group order divided by that number. Okay, so this theorem says the number of distinct elements I can reach by hitting X with elements of G is the number of distinct cosets of its stabilizer in the group G. How are we going to prove this? Well, we want to think about distinct elements we can get by hitting X with elements from our group under this action. So for elements G and H of our group, we're starting with an element X of our set. Basically, we want to know how many different things are in the orbit of X. So we should ask ourselves, if we take two elements of G and hit X with both of them, can we figure out when the results of those two things are distinct, or when they're the same, which is the same question. Okay, so we're going to think about when G applied to X and H applied to X give us different elements of S, or the same element of S. Same question, essentially. So, okay, let's suppose they're the same element. Suppose that G applied to X and H applied to X give us the same element of our set. So again, here, think of vertices as your pentagon. Take a vertex. You could have two symmetries to take that vertex to the same one. They might not necessarily be the same symmetry, but they could do the same thing to that vertex. So we're asking, when does that happen? Okay, so G.X applied, if G.X and H.X are equal to each other, we can that's an equation. We can rearrange it a bit. We can hit both sides of it with the inverse of G. Why would we do that? Well, because it allows us to express X as something else. It allows us to describe something that's in the stabilizer of X, essentially. So hit both sides here with G inverse. The left-hand side, we've got G inverse composed with G. We can compose these two because that's included in the definition of a group action. This is the identity element of G applied to X on the left, G inverse G. On the right, we've got G inverse H applied to X. Okay, so we can replace this dot with composition in the group. Okay, the group action definition tells us that. So we're saying identity applied to X is the same as G inverse H applied to X if G.X and H.X are the same. Okay, identity element applied to X is X. So this is saying that X is left alone by the application of the element G inverse H, which says exactly that G inverse H belongs to the stabilizer of X. That is saying G inverse H belongs to the stabilizer. So multiply both sides of that by G on the left, and we're saying H is G times something in the stabilizer, which is exactly saying that H belongs to the left coset of the stabilizer of X, determined by G. So here, this bit of notation, in case you've forgotten it, this stabilizer is a subgroup of G. The G on its left means we're talking about the left coset of the stabilizer of X, determined by G. That's the subset of G consisting of all elements that you can get by composing G on the left with something in the stabilizer of X. H also. So we're saying here that G of course, itself belongs to this coset. So we're saying that G.X and H.X are the same element of S if and only if G and H are in the same left coset of the stabilizer of X and G. Okay, so these two elements are the same in that case. If G and H are in the same left coset of the stabilizer, they're different if G and H are in different left cosets of the stabilizer. So what this is saying is the number of distinct elements in the orbit of X is the number of distinct left cosets of the stabilizer in G, which is exactly what we're required to prove. Okay, to read this and connect all the links requires a bit of a good fluency with all the language that we have so far, which I think can be one of the challenging things in this subject. But if you're sort of fluent in the language of index, stabilizer, cosets, and so on, hopefully it's obvious at the last line here that this is exactly what we had to prove, that the number of distinct elements in the orbit of X under the action of G is just the number of distinct left cosets of the stabilizer of X in G. That's the index of the stabilizer in the group G. Okay, so this theorem is extremely powerful. And one of the key points that it makes, which isn't written here, but it's really important, is that a consequence of this theorem is that the number of distinct elements in any orbit under the action of G is a divisor of the order of the group G itself, which is something that we can get loads of mileage out of. The number of elements in each orbit must be a divisor of G. So we know the set S is partitioned into distinct orbits by the action of G. The numbers of elements in those orbits can't be just anything. They have to be divisors of the group order because they're the index of a subgroup in the group. Okay, a special case of this, which I wanted to just mention, because it's something that we've seen before. I mean, you might even be thinking that this resembles a theorem that we've seen before. It's so-called conjugation action. So we've seen already that the number of distinct conjugates of a group element in a group is the index of the centralizer of that element in the group. It sort of resembles this Orbit-Stabilizer Theorem. So I just want to mention that that is actually a special case of the Orbit-Stabilizer Theorem, or that statement about conjugacy class sizes and centralizers can be interpreted in the language of group actions. So the action in question there is that every group G acts on the set of its own elements via the so-called conjugation action, which is defined for a pair of elements of G by just taking G dot X to be the element GX G inverse, the conjugate of X by G. So this is kind of slightly confusing the first time you see it, because here the group that's acting and the set that it's acting on have the same set of elements. Okay, the set of elements that G is acting on is actually the set of its own elements here. But we're saying that we can hit a group element X with an element G of our group. So here G is doing the acting and X is an element of the set being acted on. And we're saying that by definition, what the action does is G applying to X takes GX G inverse in the group. So it just conjugates X by G. Okay, that's an action. So the 2 points here confirm that it's an action. And the orbit of X under this action is just the set of all elements of the group G that have the form GX G inverse, where G ranges through the elements of the group. So this is exactly what we've previously called the conjugacy class of X. The stabilizer of the element X is the set of those elements G in the group for which GX G inverse is equal to X, for which G dot X is equal to X, for which this action, it's a set of the group elements that leave X alone under this action. So for which GX G inverse equals X. That's exactly the group elements that commute with X. We have a name for that. It's the centralizer of X. So under this action, the orbit of a group element, X and S, X and G is the same here. G and S are the same set. The orbit of the element X of G is the conjugacy class of X. It's the set of all things of the form GX G inverse, where X is fixed and G ranges through the group elements. The stabilizer of X is the set of G's, for which this is just X. That's the centralizer of X. So what the Orbit-Stabilizer Theorem tells us about this action is that the number of distinct conjugates of X, the number of elements in the orbit of X, is the index of the centralizer of X in G. That's something that we already knew, and the proof of that statement, which was theorem 2.2.10 in our lecture notes, bears indeed a remarkable similarity to the proof of the Orbit-Stabilizer Theorem on the last slide. So if you want to understand this really well, a nice thing to do is to compare theorem 2.2.10 of our lecture notes to the Orbit-Stabilizer Theorem, which is here in chapter 3. And also to think about exactly how this theorem 2.2.10 is the Orbit-Stabilizer Theorem applied to the conjugation action in a group. Okay, that's essentially what we have for today, except for our first challenge of week 9. And challenge 1 for week 9 is something that actually appeared on an exam paper recently, or at least versions of it have appeared in several recent exam papers. So the setup is we've got a group of order 45. It's acting on a set of 16 elements. So every element of the 45 elements of the group is moving around these 16 elements. So there are 16 factorial permutations of a group of 16 elements. 45 of them occur, well, maybe not 45 distinct ones, but each of the 45 elements of the group acts as one of those permutations. The challenge is to show that there's an element in the set whose stabilizer is the entire group. So essentially, that's to show that there's some orbit with only one element in it. Okay, so we've got 16 elements. They fall into different orbits under the action of the group. And remember, what we know about the orbits from the Orbit-Stabilizer Theorem is that the number of elements in each orbit must be a divisor of the group order. So that's the hint. That's the challenge. Thank you very much, everybody. We will see you later in the week. There's a second video coming up a little later. See you soon.